This is example 10-1, pressure drop with loss. So we have glycerine flowing through a 200 millimeter diameter pipe. It's horizontal and smooth, and it has an average velocity of 4 meters per second. And we're asked to determine the pressure drop in a 15-meter long segment of the pipe. And to start out, we'll use our energy equation. So let's write that down. Energy equation. And so we'll say that, as we say, it's going from point A to point B. So we'll say P A over gamma plus VA squared over 2G plus ZA plus H pump is equal to PB over gamma. Let's make sure we have enough space here. Plus VB squared over 2G plus ZB plus H turbine plus H loss. All right, just like we did before, we now have to go through, figure out what all these terms are. So we're given that it's a horizontal duct. So we can say, just write horizontal here. Horizontal means that ZA is equal to ZB equal to Z. Whatever you want to give it, right? They're going to cancel out if they're the same. We know that this pipe has a constant diameter. Constant diameter, which means that VA is equal to VB is equal to 4 meters per second. We're given that. We also know we have no pump and no turbine. All right, so that means we can say that H turbine is equal to H pump is equal to 0. Let's see, what else are we missing? So we want the PA and the PB, right? That's where we're looking for the pressure drop, so we'll keep those. The velocity we have, ZA we have, H pump we have, H turbine we have. So we're missing the loss term. Well, for the loss term, we know we can use Darcy-Weisbach. Darcy-Weisbach. Well, we know that is HL is equal to F times the length divided by the diameter, then times the velocity head. Let's see. In here, what are we given? We're given the length, diameter, velocity, and G, of course. What we don't know is the F. To find F, we need to find what the Reynolds number is, right? Because if it's turbulent, we have to look at the Moody diagram. If it's laminar, we can just take the number. So what is the Reynolds number? Reynolds number is, of course, the density times the velocity times the characteristic length. In a pipe, the characteristic length is the diameter. All that divided by mu. Can't plug that in. So we're saying, what are we having here? We have glycerin, so we can look up what the density of glycerin is, and that is 1,260 kilograms per cubic meters. We know the velocity is 4 meters per second, and we know the diameter 200 millimeters, so 0.2 meters. And then we can go and look up what the viscosity of glycerin is, and that is 1.5 Newton second per meter squared. Right, so this is a liquid that's already quite viscous, right? 1,000 times more viscous than water. If we plug those numbers in, we get a Reynolds number of 672. Now the critical value in a pipe is 2,300, so it is laminar, which makes it easy. So for laminar flow, we know that we get this very simple equation for our F. Right, so we had F is equal to 64 divided by the Reynolds number. And then with that, we can go back to our Dicey-Weisbach equation and plug those numbers in. So then that means we know that HL is going to be 64 over the Reynolds number here. That's the one that we just calculated, times L over D times V squared over 2G. Now if we look into our Reynolds number, maybe we just want to directly plug that in right here. So we would have 64 times mu divided by rho V D times L over D times V squared over 2G. So we can see that one of our V's cancels out. And we get 32 instead of 64 because of 2G. So we have 32 times mu times L. Now one V cancels out, so times V. Divided by rho, we get the 2D, so D squared. And we get G. Oh, it makes it a little more compact to write. So if we plug that in, I'm not sure it's going to fit, so let's go to the next line. So we'd have 32 times 1.50 Newton second per meter squared. Then we got the length, that was 15 meters. And the velocity was 4 meters per second. Divide all that by 1,260 kilograms per cubic meters times 0.2 meters squared times 9.18 meters per second squared. All right, so if I put that in, I get a head loss of 5.82496 meters. All right, let's go back to our energy equation. So the PA we're looking for, the VA we have, the ZA we have, the pump we have, the PB we're looking for, the VB we have, the ZB we have, turbine and HLOS. We have everything. So that means we can go and write our energy equation again. Now, we have, let's make that a nicer looking P here. We have PA over gamma plus, now I'll just say V because VB and VA are the same, over 2G. We said the Z's are the same. Said nothing from our pump. PB over gamma plus V squared over 2G plus Z. Nothing from a turbine, and then H loss, which we just calculated. Now we can see that our Z's cancel out and our velocity head cancels out as well. Now, if we bring PB over to the other side, then we'd have PA over gamma minus PB over gamma. And then anything left over here is HL, which means we would get that PA minus PB, which is the pressure drop, would just be gamma times HL. And we're not given gamma, but we're given rho, so rho times G times HL. It's a very strange looking H here. It's an L. Let's make that an H. HL. Now we can plug that in directly, or we have a rho into G, so they'll cancel out. So maybe we'll just write that as a full expression here, right? So we'd have rho times G times RHL. Scroll up just a little bit so we can see it. 32 mu LV. 32 mu times L times V divided by rho times D squared times G. That's what I was saying, right? Those two cancels out. So we have 32 mu L V divided by D squared. Now we could have just plugged the numbers, but always nice to have closed expressions. So that would be 32 times 1.5 Newton seconds per meter squared times 4 meters per second divided by 0.2 meters squared. This looks, oh, we're missing the L. Say it looks very short. There we go. Otherwise we're missing, yeah, missing a meter otherwise. All right, so if we plug that in, we get 72,000 Pascal. So 72.0 kilopascal is our pressure drop. Right, so we said we had a pipe that has glycerine flowing through it, and using the energy equation and the Darcy-Weisbach equation, we figured out what the pressure drop is.